Okay, now, another thing that I want you to be aware of, if you were on the AP exam given multiple trees, and I actually have a question on the take-home quiz as well, where I give you a few different trees and I ask you which one matches the data best. What you want to look for is what's called maximum parsimony. Maximum parsimony, or there's a phrase called Occam's razor, which basically says the simplest explanation is the best. And maximum parsimony, when we're talking about evolutionary trees, basically says that if a tree, we're supposed to believe that these organisms came about by evolution, then we're supposed to believe that they came about by genetic changes, mutations that happened along the way. And it's going to make more sense for there to be less changes than more changes. And it's also going to make more sense for a change to happen one time than for the same random change to happen multiple times. Now, does that mean that a change could not have happened multiple times? No, it doesn't mean that. I showed you an example in the last video about the snake and the legless lizard, and both of them lost their legs through evolution in two completely separate events. But let me show you an example of what I mean by maximum parsimony. So if you look at the cladogram, or again, it's a tree, on the left, this would be a less parsimonious cladogram than the one on the right. In other words, the one on the left is basically saying that the way that organisms 1, 3, and 2 came about, and based on this tree, is that event A happened, then event B and C happened in some order along this family line, and event B actually happened again all the way over here. So event B, whatever it is, whatever that mutation is, it happened twice. Now, that is a possibility, but if there's a way to draw this tree where event B only happens one time, like the tree on the right, A happened here, then event B happened, then event C happened, and event D happened, this tree would be the one evolutionists would say is more parsimonious, or the more correct tree, the one that makes more sense. It makes way more sense for this mutation to have happened once than to have randomly happened twice. Honestly, the easiest way to figure out the most parsimonious tree, if you're not given data to compare to, would be to literally count how many changes happened. So in tree on the left here, 1, 2, 3, 4, 5 changes had to happen. I mean, I'm literally just counting how many letters are written here. And on the tree on the right, 1, 2, 3, only 4 changes happen. So this would be the more correct tree. And if we look at the bottom, we see the same thing. The first tree here only requires 3 steps. Event 1 happened, event 2 happens here, event 3 happens here, 3 steps. For this tree B or tree C to have happened, they both require 4 steps. Not only do they require 4 steps, but they require event 3, whatever that mutation is, to happen 2 times. And if we can avoid that, we want to avoid that. Again, it is possible. If you were to see a tree and you were told it was the correct tree, and you see a particular trait 6 happen here, and trait 6 happen here as well, that is possible. Trait 6 could have happened twice. That would be an example of, remember what it's called, convergent evolution. And those would be considered analogous structures. Analogous meaning they look the same, maybe they have the same function, but they're not evolutionarily related. So that can happen, but if we can draw a tree where that doesn't happen, it's going to be a better tree. That's what we're basically saying. Okay, so a cladogram. The last thing I want to show you is how to read a cladogram and also how to make a cladogram. So a cladogram usually shows some kind of shared characteristics, and a clade is sort of a branch in a cladogram. A clade is basically the ancestor and everybody that comes after that ancestor. So I want to show you an example of what would be a clade and what's not a clade. Now, what cladograms usually show are derived characteristics or characters, meaning a particular trait that's sort of showing up along the way. So let me show you what is a clade and what is not a clade. So this would be an example of a clade. B, this point, and everything after that point would be a clade. Also, F and everything after F, or I and everything after I, or A and everything after A would be considered a valid clade in a cladogram. It includes every descendant after a certain point. So these two would not be valid clades. If we look at the one on the left, we included A, but not everybody after A. We would need to also include this side. And this one on the right, again, if it was just this, that would be okay, F and everybody after, or I and everybody after. But as soon as you highlight all of this, you have to go back to the ancestor they share, which would be A, and then everybody after A. So I'm going to switch back over real quick to the worksheet, because there's also a couple of questions where it asks if things are a clade or not a clade. So here's the worksheet again that you're supposed to do. So question 1, again, I apologize, the left is cut off there. It says, do C, D, E, and F form a clade? So if we highlight C, D, E, and F, do they go back to a single number and everything after that number is highlighted? And the answer is yes, they would be a clade. They go back to number 5 and everything after 5 is highlighted. Therefore, yes, they would be a clade. Now, how about F, G, and H? So here's F, G, and H. Do they form a clade? Well, if we go back to the ancestor that they all share, we have to go all the way back to 7. That is the last point that F, G, and H all share an ancestor. So therefore, this would not be a clade, because it would also therefore have to include everything over here. Even F and G would not be a clade, because even F and G, you would still have to go all the way back to 3 and then include everybody after that. Number 3, do A and B form a clade? Yes. A and B go back to a single ancestor and everybody after that's highlighted. And finally, A, B, C, D, E, and F. And the answer there is no, because if we look at A, B, C, D, E, F, it tracks back to 1. That's the last time they all shared an ancestor. Therefore, to make this a valid clade, we would also have to include G. So hopefully that gives you a real quick understanding of how to determine what is a clade and what is not a clade. Okay, so now when we're analyzing a cladogram, cladistic analysis meaning analyzing a cladogram, this is something that I guarantee you there'll be some questions about. So what we look for is the appearance of these new traits. A shared primitive characteristic or character is something that came about that everybody already has. Sometimes a clade or a cladogram will start with a particular characteristic. The group that's first in a cladogram is called the outgroup. That's the one that basically has the least number of characteristics. Usually, a lot of times I should say, that one doesn't have any of the characteristics that are in the cladogram. It's sort of the ancestor to everybody. And then a derived character, so a primitive character is something everybody shares. Where's primitive character? And then a derived character is a characteristic that is unique and new to a particular clade. So let me show you what I mean. So on the left we have a matrix. Don't let the matrix scare you. Here on the top are the names of the organisms, and on the side are the characteristics. So the lancelet, they tell you, is the outgroup. From this, you can tell, because if you look at every characteristic, notice the lancelet doesn't have any of them. He has zeros. A 1 means they have it, a 0 means they don't. So the lancelet is our outgroup, and in this picture, you see him here. Notice he doesn't have any of the characteristics in this cladogram. And then as we go through, we can see that the first characteristic everybody else shares is a vertebral column or a backbone. And then everybody after this point has the backbone. Everybody after this point has the backbone plus jaws. So you could be asked a question like, what characteristics do the turtle and the bass both share? So what you would have to do is track back to where the turtle and the bass connect, which is here, and the characteristics they both share would be everything up to, prior to where they diverge. So jaws and a vertebral column. Here's another example of a cladogram. So in this one, I could ask, what is the outgroup? And your answer would be the hagfish. The hagfish would be the outgroup because he's first, and he doesn't share any characteristics at all. He comes before the first characteristic. Also notice that it's possible for a characteristic to be only unique to one organism. So the feathers, if you'll notice, are on the branch here for the pigeon. And again, I could ask you, what characteristics do the pigeon and the salamander share? You would track back to where they connect, pigeon and salamander. The characteristics they would share, therefore, would be lungs and jaws. Everything up to the point where they diverge from each other. So that's how you read a cladogram. Now, the next thing is how to make one. So making a cladogram, I'm actually going to skip and do this one. So this is a real simple one, and this is probably more like what you'd see on the AP exam anyway. So you'll notice organisms here on the left, and then characteristics at the top on this cladogram. So what you want to start with is you either want to find a characteristic that everybody shares, so a characteristic that everybody has, or an organism that doesn't have any. You can't have both of these things. So in this particular cladogram, if you'll notice, I have an organism that doesn't have any of my characteristics, moss. It has all negatives. So moss will be my first organism in my cladogram. It would look like this, moss. Now I'm going to draw a line. Now that I've crossed off moss, the way you're going to do this is you're going to go horizontal. Now that we've crossed off an organism, we're going to now go vertical and see what's the next characteristic, or what's the first characteristic that everybody after moss has. And you'll notice that would be vascular tissue. Everybody after moss, because we've crossed moss off, has vascular tissue. So that's going to come next, right here. Vascular tissue would be our first characteristic. Everybody has that. Now we're going to cross that off, and we're going to go back to horizontal. So notice we did an organism. Now we did a characteristic. Now we're going back to organisms again. Is there an organism that now has all zeros or all negatives after vascular tissue? And yes, there is. Ferns. Notice how the fern doesn't have any characteristics after vascular tissue. So fern would be my next organism that I would add to my cladogram. And now I'm going to cross off fern. Now I'm going to go vertical again. What's the next characteristic that everybody else that's left all has? And that would be flowers. So the next characteristic in my cladogram is flowers. So there's my fern. Now I'm going to cross off the characteristic of flowers. What organism comes next? Going back to my side, look, pine trees. Pine trees does not have anything beyond the characteristic of flowers, and so pine trees go here. Now we go back. What's our next? We just did an organism, so characteristic. Sorry. And the next characteristic is the only one left is seeds. And last would then be flowering plants. Now we can double check this. Does flowering plants, or do flowering plants have seeds, flowers, and vascular tissue? And they do. Flowering plants have all three. Do pine trees have just flowers and vascular tissue? Pine trees, vascular tissue, flowers, no seeds, yes. And so that's how you make a cladogram. You go back and forth. I'll show you one more. This one was actually on the AP exam. This one they actually had you make a tree. Notice this one has organisms on the top and the side, which kind of looks screwy, but this one, they explained that this is the number of differences in a particular amino acid sequence. So in other words, the donkey and the horse only had one difference in their amino acids. What other two organisms have a very low number there? Well, if we look, you'll see here the penguin and the chicken also have very few differences. What organism has the most differences from everybody else? The snake. He has 21 differences from the horse, 20 from the donkey, 18 from the chicken, and 17 from the penguin. So this one's a little weird, but that year on the AP exam, they asked you to draw a tree. It could be any tree. All you really had to do was something like this. The snake would be not very closely related. The horse and the donkey would be very closely related because they only had one amino acid difference. And then the penguin and the chicken would be somewhere in here. Penguin and the chicken. It literally could look anything like that. It didn't have to be straight. It didn't have to go exactly that way. But as long as it somehow showed that the snake was further away and that the penguin and the chicken were close to one another and the horse and the donkey were close to one another, you got credit for it. This is another one that was just a couple of years ago. They gave you this and they just asked you, they explained it, that it had to do with milk components. And all you had to do was fill in the organisms. And if you notice, the cow, the horse, and the pig all have the exact same, they all have protein A, protein B, casein, and lactose. So you just had to put horse, cow and pig together, and then the cow